I'm sorry about that. I'm Pranava. This is a joint work with Josiah and Lucia from University of Sheffield. So we sort of have this claim, end-to-end image captioning exploits distributional similarity. So, so the setup is this. So we have an image, and we want to describe the image. So the typical approach that is prevalent right now is you pass an image, get a vector for an image, which sort of is using a pre-trained CNN network. So you get a vector, and you sort of project the vector if you want to, depending on the size of the RNN, and then pass it on as the initial state for the RNN generator. So that generates a description. So that's the setting. We are really interested in the transfer. So we are sort of transferring information from an image domain to a sort of a text domain. So are we really transferring, is that an optimal transfer, or how much is it that we are transferring the information content? So I basically come from an NLP field mostly, and we have sort of a problem here. So if we sort of take a sentence and sort of represent that sentence using a vector, we are frowned upon. So Raymond Mooney from UT Austin says you can't cram the meaning of the whole sentence into a single vector. If that's true, and we know that the picture probably speaks 1,000 words, in the sense picture is probably more richer and image is more richer, can we sort of represent that by a single vector? That's the question that we really focus on. So we are interested in what is really being transferred. So we want to investigate the representational contributions of the images. So is 2048-dimensional vector from a ResNet, say, enough? So what we are really interested in is we vary the input representations and see the effect in the task of captioning, so generation of some kind of language. And we try to have some kind of control and see if that makes sense. And we try and visualize the learned space and the initial space, and we see if we can get some insights into it. So the playground is basically the same thing that I mentioned before. You have an image, throw in a CNN, get a vector, and see different kinds of vectors that you can get, and push it into the initial state of the RNN and generate a sentence. You train it on a parallel data set and try generating sentences. This is sort of a resilient architecture. It's being used even now, and people, the state-of-the-art approach is sort of actually modify, so engineer the language content and try to sort of optimize the generation. So the classic approach is you take an image, pass it through your CNN, go to the penultimate layer, typically in ResNet, say the average pooled representations, or in the VGG, there is a bottleneck layer, and you sort of extract the representations, pass it on, initialize your RNN, and sort of get the description, and measure the description using 5 reference captions which were generated by humans. So there are different scores. What people usually use is CIDR, which is one of the scores which is pretty common for measuring these. It's an n-gram-based score. So you basically measure the number of words which are common and the sequence of words which are common, so the n-grams which are common in the generated language, or the generated description, and the reference description. So this is sort of the score that we get. If you use a VGG, you sort of get 0.69. If you use ResNet, you sort of get 0.74. So people sort of stick to ResNet and do a lot of modifications on the language side. So what really happens? So if you take ResNet and do a t-SNE, I think most of you probably know about this, you sort of get these nice clusters. So you get these clusters in here. You have clusters of men, humans on the snow sort of doing something, and there are also animals in the snow doing something. It sort of clusters things with snow together. That's pretty interesting. Then we say, okay, so what happens with the posteriors, the class posteriors? You have 1,000 classes, you do ImageNet, then you basically have you train a multi-label classifier. So what happens with this? So the data set is MS Coco, so there's not much overlap over there. And we see that the pool 5 representations versus the posteriors, there's a huge drop. And that's sort of okay, because if you see really the initial representations, plot them in, and see what is it look like. So typically, some of these cluster pretty okay, but most of them are basically clustered together because it doesn't know what's happening, so it doesn't have much clues. So nothing happens over there. So the initial representation was not good, so we didn't get the good results. So the other things that we investigate is MS Coco is a good data set in the sense that they have around 80 object categories which are annotated by humans, so there are bounding box or segmentations for 80 objects. And we say, okay, let's try a very simple representation where we just represent the image using the objects that are there in the image. So typically, this happens to be a very sparse vector. So in this image, there are only 2 objects. So there's a man and a skateboard. These are the kinds of representations that we sort of initialize. We see that if we just do that, so that's the pool 5, just by using this very sparse representation, we sort of get a significant gain, a boost. Again, by using bag of objects and frequency. So there is, I mean, we do not, there is nothing called an order. So it's just mention the objects or mention the number of times those objects appear. Again, that sort of goes up, it shoots up to 0.81. That's pretty high. So this was really interesting, and then we asked the question, okay, if this is true, what if we remove one of these objects? So we have all these, it's a parallel data almost. So you have an image, you have the language, the caption that describes that image. So we remove the information about the man and train again, and we see it doesn't drop much. And that's interesting. So how does the representation, if we sort of do a t-SNE on 2-dimensional and sort of plot it, we sort of get these nice kinds of clusters again. So in this small cluster, there are better clusters in the paper and the link in the paper. But in this cluster, it's basically about sinks, because sink is one of these categories which is mentioned in the MS Coco. But if you see, there are sinks which are kitchen sinks and bathroom sinks. So I'll come to that again. So this so we asked the question, okay, if this is true, let's try investigating a little bit more deeper. So what we said is, okay, per object, we'll use a random vector. It's just a random vector per object, and we just sum these. Suppose you have 4 objects in the image, we just sum them up. And then we take this random, it's sort of a pseudo-random in the sense that it consists some information, but it really has to disentangle this composition to actually understand that there were 4 objects involved. So we just sum them up and then pass it on. That's pool 5. There is a small drop if you don't include the frequency information. If you include the frequency information, that is 4 times a random vector for object of a man, plus, say, there was a skateboard, so 1 time the skateboard. So that's the representation. You just sum them up, that's the representation. And it seems like, well, that's also performing pretty good. So this is really weird. So if you really look at the random representation, the pseudo-random representation, they are they are almost random. There is no cluster over here. These are just a bunch of random images sort of clustered together. That doesn't make any sense. So if you see this course again, so pool 5 is one of the traditional sort of representations that people use. ResNet, pool 5, initialize the RNN. Posteriors, yes, there is a significant drop. Bag of objects, there is a slight gain. Bag of objects for frequency, there is a significant gain. And then the pseudo-random and pseudo-random plus frequency, again, it sort of is performing very similar to the bag of objects and bag of objects plus frequency. So this sort of, so then we ask a question, okay, so we know there are 80 objects that were sort of annotated. Let's do one thing. Let's take the pool 5 vectors, and then can we sort of compress them? So compressing in the sense, what we do is just do a PCA, project it to an 80-dimensional representation, use that 80-dimensional representation. So we try 2-factor, there are 3 different kinds of factorization techniques. We try PCA, probabilistic PCA, And so the initial representations were 2048 dimensional. It was projected to 80 dimensional. And just by doing that, the score goes up. So again, this is sort of interesting. I mean, why would this happen? So the hypothesis when you do image captioning is that you are trying to understand what an image is, and probably then you'll be able to describe it. So that's the setup, but so far, this doesn't seem to lead us to that conclusion. So there are two different, I mean, there are many data sets for image captioning. There are two that we try. We say we train a model with MS-COCO data set, parallel MS-COCO data set. And the trained model, we test it on Flickr. Now, the data sets, the vocabulary overlap is pretty good. It's almost 90% of the vocabulary is common. There are some syntactic differences because the way the captions were collected was slightly different. The rules that were used were slightly different. Still, what we see is a model which is trained on MS-COCO doesn't generalize over Flickr. Especially, even the words themselves are not, the overlap in the blue one is the score for a unigram overlap between the word that is generated and the references. That seems to be low as well. So the TDBU is top-down, bottom-up, a state-of-the-art captioning model, which was presented last year at CVPR. We use that, same kind of results. So this applies a lot of image-oriented as well as language-oriented engineering, and they get significantly huge gains on the MS-COCO data set, but they drop significantly over the Flickr data set. So this is a very slight domain mismatch, but we have a problem there. So what does this lead to? So the main conclusions that we have is what we are doing in image captioning is to an extent applying the distributional hypothesis that a similar sort of vectors in the image area and similar sort of sentences in the language sort of are, you do some kind of a nearest neighbor search, even if you use these kinds of end-to-end approaches. So models are basically exploiting the distribution of the data. And this is sort of a good, bad thing or good thing, I don't know. But then what really happens is, so we take this vector, the image vector, and we transform it to the dimensionality of the RNN generator. So hidden representation, hidden dimensions of the RNN generator. So you have a 2048 dimensional representation. We learn a transformation which transforms that into one, say, 256 dimensional representation in our case. So this was before. What happens after the transformation is, again, some kind of distributional information percolates. So what's happening over there is all the animal-related stuff. Since whenever there is an animal in the snow, people have to mention the animal. That's what people do. Whenever there's a man who's doing some kind of action, people actually mention that man and the action in the description. So that it sort of percolates over there, and the clusters sort of move. They change. Similar thing happens over here. You have sinks which are there in different rooms, transformed. The sinks are separated. Now you only have sinks which are there in a bathroom, which are separated from the sinks in the kitchen, because people usually mention, whenever a sink is in a kitchen, they mention kitchen explicitly. Weirdly, in the pseudo-random case, it actually is like this in the initial representational space. As soon as that's done, it actually cleanses it up. So we see beautiful clusters in this transform space. So, so what could this lead to? Well, image understanding right now is almost like a signature matching thing that we are doing right now. So we are not really, I mean, at least for image captioning, we are not really doing image understanding and then captioning. So CNN representations do provide neat signatures, but I'm not sure that's the optimal representations for transfer. So with that, thank you.
Any questions, please? Come on. You gotta be depressed by these results. It seems that nothing is working. Just I feel depressed. So is it true nothing is working? Should we all pack it up?
Well,
go to the beach?
I mean, it works on that data set, so it's fine if you have similar kind of distributions of the language and your images. But that's...
I mean, the presentation tone was more pleasing than the paper tone. The paper, I read it, I was like, wow, damn it. I want my money back. Anybody, read the paper. Any questions? All right, let's thank him again. So the next speaker is Wei Fei from Oxford. He's actually representing some of his friends who couldn't come here for several reasons. On the paper, boosting up scene text detectors with guided CNN. And it should come up. Technology. I hate it. There we go. Thank you.
Can you hear me? Okay, thanks for the introduction. So actually, this is my friend's work, and they can't be here, and I'm not one of the authors. So I got this notice very shortly. So, and I'm not expert in text either. So it's like more like a reading group thing, because we read the paper basically together. And this work, it's about the text detection. So you may ask, I think you know the application. We have text everywhere, and if you want to do autonomous driving, you need to recognize the symbols on the road. And if you go to the restaurant, you need it, especially if you go to other countries, non-English speaking or something, or you just don't know the language. And also, this is about detection. So you may ask, okay, object detection works just so well, so why bother text detection? I think it's really because there are problems, there are different problems, because for text detection, the text could be any shape, it could be curved. So in the object detection, people use bounding box, but here you can't use them. Well, you can, but the performance will not be good. That's the one reason. And the second reason is, if you want to detect an elephant, you know it's elephant, that's all. You don't need to know, okay, which elephant it is. But in text, it's like more fine-grained. So the problems then is accuracy and speed are both important. So in this work, the motivation of this work is they found, okay, in the scene, if you look at the whole, you know we have text here. It appears very sparsely. So like these statistics is from a data set called ICDAR 2013, and they did the statistics. So you can see only 5% of the image, they have 40% to 100% of the text. So it's very small amount of images have text. Okay, so if we want to speed up the detection, then one of the ideas come out, maybe something like cascade. So if we can do some rough filtering of the background, get rid of the background, and only focus on the foreground, then that will be much faster. So that's the key motivation about this work, well, I think. And so what they do is you have an image, you just give a guidance subnetwork. So this subnetwork should be very lightweight because you need it to be very fast. And also, you want the recall to be very high. You don't want to miss the text. You can include some background, that's fine, because you have a second step, but you don't want to miss. So that's why it needs very high recall. And also, the text detection is really just a binary problem. It's either text or background. So if you do this kind of mask thing, it could be any shape. It doesn't necessarily to be a bounding box. So you can think of this as a soft version of mask RCN, something like that. And you have the red box there. that's going to be your main text detector. That could be very heavy because after you filter out your background, your foreground is really just a tiny amount, and you can do heavy processing on them. Still, your speed will be okay. And this is the guidance subnetwork. Like I said, they want it to be lightweight, so they use the PVA net, which was developed for the object detection very fast. And also, like I said, the shape could be really weird, so you possibly need to include some contextual information. You want to increase your receptive field of your CNN because you don't know what the shape of the text, and you need those contextual information. So if you see this contact module, it's basically like FCN. You do downsampling and you do conv, you do another downsampling conv, and upsampling just concat, or I think they do add. So they fuse the information by adding. And they do some experiment to show if it's useful to use the contextual information. So as you can see, the second row of the left column, that's the result without the context module. And you can see some of the small text, they miss it. Or it can just include some rubbish backgrounds, like the plain symbol. It's not text, but sometimes it looks like text. But if you have the context module, you can filter them out, and you get back the small text. So basically, they show it's useful. And that's how it can speed up. So if you have the first step done, you have the mask, which is a soft version of the mask, and you just need the mask and the image. You can do the image column, not every patch. You just do the image column based on the mask. So you can get them out and do the filtering, do the dot product only on them. So that could accelerate a lot, especially on the CPU, actually, because the operation just drops a lot. And after you do that, you just put them back because you know the mask, so you know where these values should be put back. So that's the reorder process. And so during training, they found some problems. One of the problems is if you only train with the text bounding box, you can't obtain the result with very high recall. So that's one of the problems they found. And the way they solve that is by doing some random, say, the red box, you see them, that's the random boxes on every image. And those patches, they treat it as the positive class, meaning treat it as text, because those are random. So you can think of them like slightly like dropout, and it just solves your overfitting problems a bit. And they also show it's useful later in their experiments, actually. And these are the training strategy they show, like I explained. Well, basically, they show it's useful. So they use the baseline, which is called CTPN. It's published in 2016 ECCV. And the problem with that model is, well, that model is still very good. But the problem is they use LSTM, so across the whole image. So it's very computationally expensive. So that's why, but the performance is good, but just too expensive. So that's why they want to speed it up. And by doing this guided thing, you can speed it up because you just need to process very small regions. It doesn't matter, it's LSTM, RNN, or whatever. You can use very heavy models. And so the baseline CTPN is the left corner, which is the diamond. And their result is the square. So they are better, the higher the better, both recall and precision. And these are the experiments they did. So they show on several different data sets. And as I said, the main thing is really, it's about speed up. So you can see the speed up. They achieve like 4 times faster, while the performance is comparable or even sometimes better. So that's I guess that's the good thing. And more experiments, of course, state of that. And results, qualitative results. Thank you.
Let's thank Wei-Fei. He gave the very good presentation, very fast, and he didn't panic on something that probably he didn't know. Actually, good job.
Thank you, thank you.
So let's make his life a bit harder. Let's ask him one question that at least he can intuitively answer without having to call his friends. Come on, help me.
Thanks. Thank you very much.
So our next speaker is Ahmed Kedir. He's coming from Norway. He's going to present YNet, a deep convolutional neural network for polyp detection. If you're strictly stuck with computer vision, you may see some images that may not look very nice. So, I warned you.
Okay, thank you very much. So I'll take you to medical domain in my presentation. So this work is done by Ahmed, Shule, Ivar, Marius, and Øystein Hovde from NTNU and the University of Oslo. So I will go through this outline. So maybe I will just give a background to medical imaging in case some of you don't have the background. So a colorectal cancer or tumor is basically it's a tumor or it's a cancer that grows inside your colon. So you have different type of diseases inside the colon. It could be ulcerative colitis or Crohn's disease, and these things need to be detected early on, otherwise it will cause a tumor or late stage colon cancer. So detection of this thing is have been a goal for a long time. So they are the third deadly cancers so far, and screening the population is very important, especially if you are above age 50 or something like that. So the colon part is the one that is marked by black. So basically the way these videos are obtained is the doctor inserts a camera and it tries to see using a colonoscope. So that's how the videos are obtained. So detection of these problems is different from natural images because you have different type of polyps. They don't have any specific appearance. So for example, you have neoplastic and hyperplastic polyps, but hyperplastic, you don't want to detect them. There are still some mass of, is a mass that's grown, but it doesn't turn to a colon cancer, so you don't want to detect that one. What you want to detect is a neoplastic one. And you also have this peduncated one, what most people know, the one that have shorter base and larger surface area. That is like mushroom type growth. And you also have like sessile, the one that have large surface that covers the whole region as a polyp. So you have a lot of appearance variation, orientation, shape variability, and it's not easier to train a network to detect these diseases. And also when the doctors investigate, they sometimes, because this procedure is time consuming, they do fast inspection, which leads to misdetection, especially if you have small polyps less than 6 centimeter, there will be a miss rate of like 30%. So automatic detection systems are very crucial. So I hope you get the motivation of the work. Yeah. So there have been a lot of work that have been done in this area. So, some of the work include early on with handcrafted feature, but the idea is basically you try to model a polyp using a valley type of approximation. So what you do is you try to do intensity valley detection because they look like a mushroom. But the problem with this one is they give high false positives, so that means the doctor needs to see them again. So they don't improve a lot of time. They don't save time for the doctor. So there have been deep learning approaches in this area as well. So there are been like CNN with RGB input, geometric features, like as additional feature map in addition to the RGB input image. There have been transfer learning, training from scratch. Different methods have been tried, and also the 3D convolutions. But one disadvantage of this field is there is not enough data. So you can't train like large deep networks. So that have been the main problems in training more networks. So our objective is to try to detect using RGB image as measured in F1 and F2 score, because you want to have high recall. Otherwise, if the polyp is missed, it will grow as a tumor, then the person will be in danger. So you need to have some high recall classification or detection mechanism. So we are more focused on the harmonic mean of precision recall, which is measured in F1 score. So there have been multiple empirical evidences that shows that transfer learning give good results when you have the inputs and the target distributions are similar, the data distributions are similar. And training from scratch works in case you have very small samples. That's shown in, I think, the paper that came out in May from Google. So our approach is we try to exploit transfer learning as well as training from scratch. So the main idea is to address the domain shift, because when you do transfer learning, the main image that is we used is ImageNet, and it is very far from the polyp data. So you will have domain shift problem. So our idea is inspired by such kind of architectures, encoder-decoder, but all of these encoders and decoder architecture, what they have is they have some sort of skip connection that shorten the path between the input and the output. So that's why then you have a better gradient propagation and you get a good result. So, but since we don't have more data, so we try to devise a mechanism to use ensemble of encoders rather than a single encoder. So our approach, we start with a pre-trained model, VGG or ResNet block. So for this work, we used VGG. And what we did is, the first one is VGG pre-trained model, and then the next one is untrained VGG model. So, but the thing is, we introduce here when each encoders are trained, each encoder is run with encoder-specific learning rate. So because the pre-trained model have already an ability to detect lower layer features like edges and those things, we want to keep those features. So the top layer is learning with a much slower learning rate compared to this training from scratch one. So that basically you have more robust feature representation. Then what we did is, once we have that one, we skipped the summation of each feature from the multiple encoders into the output decoder, so like normal skip connection. Then at the final output, we have the mask for the polyp. So then we used the normal loss, which is the binary cross entropy, and the dice loss coefficient as a loss function. So for testing, what we use is ASU Mayo dataset, which has 20 training set and 18 short segment test set. And out of that one, 4,728 in training set have polyps, and 4,300 in test set. So if you compare, we compare our result with new 3D convolutions and also Nikkei challenge in 2015, and our result is almost 10% better than the previous approach. So we specifically focus on the recall because we don't want to miss a polyp. And also, if you consider F1 score or F2 score, we have a much higher result comparatively. So we have also the lowest number of false negatives and the highest number of true positives. And the baseline for this study is like, for example, you can say like what is the advantage, or you are over-parameterizing the model. So what we did is we compare, for example, unit with pre-trained VGG with single encoder, still our meter performs the best. So, okay, before I go there, hope it works, yeah. So this is the real video. I hope you guys doesn't give you low appetite for lunch. So the proposed, this is from the test set, the test set sample video. And yeah, so the top row, the top 3 rows show the best, the correct detections, but we also have some problems in the detections. So the green boxes are the ones that are detected as true positives, but there is no polyp. There is a lot of structural similarity, especially, for example, you have a region when you start at the start of the colon. Yeah, so you have this polyp-looking structures, so that's also one challenge that we try to address. And also there is a misdetection. Like, for example, here there is a polyp, but our method is not able to detect because there is a lot of variations, but still our method is better than the state-of-the-art. So thank you very much. If you have questions, please.
So questions from the audience? Then I'll ask them some.
It could be medical related as well.
I'm
not
any
medical
question?
doctor, sorry.
Any question? So is there any incentive of including some temporal information, or the scope goes very fast and it doesn't matter?
Yeah, we tried to include temporal information so we investigated that, but we didn't get any significant improvement with that approach.
Okay.
But with LSTM, I didn't try with LSTM type, but with the convolutional different way of mixing temporal information, we tried that one.
Okay. And my understanding is that the data set actually has the segmentation maps.
Yes.
But yet your results show the results on the performance on the bounding box. Is that correct?
Yeah, so...
You don't have any dice score segmentation results.
So on the paper, on the Mikai challenge, there are 2 problems. The first is detection and localization.
Okay.
So the main purpose of this one is on detection part, yes.
All right.
Yeah.
Any questions again? All right. Thank you very much.
Thank you very much.
We are switching themes from the medical to the musical. It's true, it's true. The next paper is guitar music transcription from silent video from Shir Goldstein from Israel. I tried to learn guitar. Yeah, I became an academic instead. So Shir, the floor is yours.
So, hi everyone. Thanks for sticking around. My name is Shir, and I'm presenting our work, guitar music transcription from silent video, done by myself and my advisor, Yoel Moses, and we're from IDC Israel. So, imagine that you're lucky enough to be seated in an Eric Clapton concert, and he plays this amazing solo, and you're really anxious to go home and try to do it yourself on your own guitar. Well, the problem is, this is you. And maybe you're not quite of a Mozart, and you're not quite able to hear a musical piece only once and be able to repeat it flawlessly. Luckily, someone has written down the musical sheet for you. But problem is, not all composers write down their music. So a skilled musician is required to listen to the musical piece and write down the notes. And problem is, it's not a trivial task. It can be time-consuming and tedious, and especially when the degree of polyphony rises, it's harder. So, an automatic mechanisms were introduced where a computer gets an input of an audio signal, and the output is the musical sheet. So it works quite well for monophonic music, but again, for polyphonic music, it performs below human skills, which is unfortunate since most music is polyphonic. And the basic technique here was introduced to us about 200 years ago, which is called the discrete Fourier transform, which basically takes the signal and transforms it to the frequency domain and finds out what frequencies make up the signal. So we take an audio signal and we do the transform, and then we have the frequency information. And this is very suitable for our case, since notes are basically frequencies, and so we are able to find out what notes are being played. So, spoiler alert, we're going to try to solve some of the limitations that I talked about using, well, computer vision. The first reason is that vision is very fun, as you all know. And also because I'm going to show you that it can solve some ambiguities that arise from audio-based methods. So obviously there's a lot of information in silent videos. But I'm going to show that for this set of videos, we're not only able to say that there are guitars playing here, but to actually say the notes that are being played. And actually those videos are the input for our methods. The setup here is GoPro camera mounted on the guitar that is being played. And our task is to look at that video and say what notes are being played every time to build a coherent musical sheet. So what's the basic idea here? So a basic idea as presented by Wu et al. In 2012 is to look at a specific spatial location, a pixel that is close to the string. And we're going to take the signal of change in intensities in this specific pixel, and we treat it as a time series. And we look at the change in intensity. And they showed, which is kind of obvious, that the frequency information we have in this signal correlates with the frequency of the string vibration, and which is the sound, the note we are hearing. And so we're going to use basically the same tools as in audio, which is the discrete Fourier transform. We're going to take the change in intensity signal and see what information there is in the frequency domain. So let's go over our method outline. So first of all, we need to obtain those pixels that are near the string. We call those string pixels. And then for each one of these, we will have a signal. Then we can go about analyzing those signals in musical context. So first we have the temporal segmentation, which is actually to say when a note is being played, when does it start and then when does it end. And then once we have the temporal information, we can actually say what is the note that is being played. So let's first talk about the string pixel detection. So as computer vision people, we probably would have taken some edge image and say, well, pixel on edges are probably near a string. But we propose a different approach. Actually, we do some calibration process. Actually, we play a specific note on a string, predefined note F, and then we apply discrete Fourier transform on each of the pixels in the frame. So we expect pixels that are not near a string to have low energies for the frequency we played, right? Because there's no frequency information there. But for pixels that are near the string in yellow, as you can see here, there will be high energies for this F. So then we can filter out those frequencies with low energies and just keep frequencies on the string, near the string. And we keep a subset of those pixels, and actually we obtain the signals from each of those marked pixels. So we have multiple signals for each string. So now we have multiple signals for each string, and now we go about to analyze them. Then we will do for both next step some kind of a majority voting to actually say what is the temporal segmentation and the pitch detection. So first, we do the temporal segmentation. And the thing we want to know here is to find temporal window where a single note is being played. So how do we do that? We use a spectrogram that uses a short-term Fourier transform. Short-term Fourier transform is actually just to break down the long signal to small temporal windows and apply the discrete Fourier transform we talked about earlier, and then to form some kind of a map which every column in this map is a single single Fourier transform. So the x-axis here is the time, and the y-axis is the frequency, and so we can see the dominant frequencies along time. So actually what we want to do next is to segment those high energy regions, and in order to obtain a single note. And since, again, we're analyzing each string separately, only one note can be played at most at a given time. So we first segment the spectral high energies, and then we're able to discard temporal overlapping segments. So once we obtain the temporal information, we can find what note is actually being played in this temporal segment. So as I said before, we now know the time where there is a single note, and we can apply, again, discrete Fourier transform on it. And we expect to see a peak in the frequency domain for the frequency of the note. However, as you can see here, this is what you get. You get several peaks in the frequency domain. Those peaks are actually because notes not consist only from a single frequency, but from a fundamental frequency and harmonics, which are integer multiple of the fundamental frequency. So the peaks we will see are either fundamental frequency or harmonics. However, we do have some bad news. According to Shannon-Nyquist's theorem, we can only perfectly reconstruct frequencies that are below half our sample rate. And since our sample rate is 240 frames per second, and guitar's frequencies are much higher than that, our frame rate is actually too low. Just to state that audio has about 200 times more sample rate than we. So they have no problem with that. So how will we solve that? We're not giving up. So for frequencies above 120, there exists a frequency that we will see in the frequency domain, and it is called the alias frequency. So each of the peaks we will see in the frequency domain are either the fundamental frequency and the harmonics we talked about before, or aliased frequencies of one of the above. So, for example, this is a Fourier transform applied on a single temporal segment. And now we can use the fact that we know what string we are playing on. So there's a set of pre-known notes that can be produced using this string. So the thing we do here is we match each one of those notes to the response we got in the frequency domain. So for example, as you can see here, this is the note E1, and it doesn't match quite as well. What you see here are the frequency component of the note. The big one is the fundamental frequency, and the other are harmonics. But for G sharp, this works better. It matches better. So we're probably going to say this is G sharp. So not all is good with aliasing. We do have some ambiguities, and one of the ambiguities are notes that are on the same string and are indistinguishable from one another. So there are notes that are, well, different. They have different frequency components, as you can see, but because of the low frame rate, they are aliased to the same frequency components. So we won't be able to tell them apart. Another thing are frequencies that are aliases to low frequencies, and we consider them within the noise range. So again, we won't be able to see them. So let's talk about how we did the experiments and how we evaluated our method. First of all, the data was collected by us, actually by me, and somehow I convinced my advisor that me filming myself playing the guitar is good enough for a master's degree. So we played on 4 different guitars, including bass guitars, and we played the chromatic scale on each string several times. The chromatic scale is basically just playing consecutive notes one after another. It is maybe trivial to play, but it doesn't trivialize the problem, so that's okay. And also we've thrown in some melodies and chords just to have a lot of fun. So for the pitch detection part, we were able to achieve about 67% correct. We used both the computed temporal intervals for a method, and also we fed the ground truth temporal intervals and checked our pitch detection part by itself. And as you can see here, this is a visualization of the results. So the x-axis here is time, and the y-axis is frequency, and each rectangle corresponds to a single node. So we want the red ones, which is the results from our method, to align with the blue ones in the x-axis and also in the y-axis. And again, as I said before, the yellow ones are the results of the pitch detection when fed with the ground truth temporal intervals. So you can see if the temporal intervals are correct, sometimes the pitch detection works better. So about onset evaluation, which is the start of the node, the start of the temporal intervals, we consider a node to be correct if it is within third of a second of the ground truth. And we obtain 0.9 in F measure. It is important to note that state-of-the-art audio performs 0.87, but those results are not really comparable since it's entirely different data set, and they use other instruments, percussion instruments, for example, and we are restricted to the guitar. So here we quickly just demonstrate, this is a preliminary test to show that our method combined with audio-based method can actually eliminate a lot of ambiguities that arise from audio. And before we wrap up, I just want to mention that there are some other visual-based automatic solutions, but the main thing they do is to look at the left hand of the guitar player and to try to position it in relation to the guitar. And the main problem is that they don't actually have any temporal information because they only track the left hand and not the strumming hand. To conclude, we're the first one to use the string vibration for automatic music transcription. And although our method we're not perfect yet, but we do have some promising future directions. Our method is physics-based, so no learning here. And for future work, there are a lot of directions to go to, a lot of post-processing to do, maybe to analyze it in musical context. But one of the most promising future work is to combine both audio and video. And here's an illustration of us working on the project. And thank you for listening.
Thank you, Cher, for the paper. It's my background is in signal processing, so it's refreshing to, for once in a while, use the Fourier and see it actually working so nice. Questions? A guitar player in the audience. I know at least two. I'm not going to call on them. Yeah, you go. Thank you, Tony. Yeah.
Do you think you'll be able to pick up things like bends and slides with this sort of approach?
Like more rock stuff.
More rock stuff.
Yeah. Right?
Actually, there are some guitar players, mainly rock stars, that play with a GoPro mounted on the guitar. It's very cool. So, wanted to say something? Oh, yeah. No, okay. So I think, yeah, maybe, the vision is that you're going to sit in a concert, and by the time you get home, you get the musical sheet ready, just filming your favorite rock star. But yeah, the thing is, automatic music transcription is very important. It's a real research field in music information retrieval area. So we want to do better. So if you can use some visual information to solve the ambiguities,
I think the question is, will you be able to get the transitions when you do the,
Oh, okay.
That sounds like, is like a note for that?
Sorry?
Is it like a note for like, in like air guitaring? No?
Yeah, there's a lot of, I don't know, there's tremolo for other string instruments. There's a lot of different techniques. So probably we won't be able to use, the fact that there's a known preset that you can do on, you can...
So you're obviously not a blues guitar player, but you studied
Yeah.
Clapton, yeah? So what Clapton does a lot is hold a note, hit it, and then bend the string upwards.
Yeah.
Yeah?
I know what you mean.
wondered if you'd pick that up, that was all.
it should, you know, when the string vibrates, it's what you hear eventually. So you should be able to recover this vibration. The thing is, you probably won't be able to just have a preset of known notes that you can that you know that you can play on the specific string. Maybe there's another preset of blues players that they can extract from the guitar.
Anybody else? So go home, pick up the guitar, take a GoPro, play some notes, and share the data. Then she can do a better project. Even better and better and better. All right, let's thank Shir.
Thank you.
I promise you there is only more 15 minutes of me. The session is almost over. So the last talk is image retrieval with mixed initiative and multimodal feedback by Niels Murugara from Pittsburgh. While we're fixing the technical problem, what did you do in Newcastle? Was it fun? Sorry, I only came just today. How was the banquet? Was it good? Did you have Newcastle beer? Huh? Wine mostly. That's good. Newcastle is known for having a very nice nightlife. I know it's been a long time since I used to do these things. So I know after we have the lunch, and then after there is the last keynote by Rama Chalapa, so that should be very exciting. And then we also have the workshops. Probably I'm actually stealing the thunder from the actual organizers by saying all this, but for some reason we gotta kill the time. And my stand-up routines are not good anymore. I hate technology. I really hate it. I know. I mean, that's this guy's job to fix that, but I don't envy him. These computers, can we just standardize them? Can we just all buy one thing? I did my thesis with like the slides. Do you remember that we used to print them on a transparent paper? Nothing can go wrong then. Well, okay. Oh, no. The light can go out. That's fun. Then you have to have a flashlight. Do you want to do some announcements?
For the moment now.
Yeah, please.
Yes. So I'll just step in and learn something while there's a gap here. So when this session finished, you can go upstairs and grab your lunch. So today's lunch will not be at the Civic Center. It will be here. So if you go around there will be nothing there for you. Don't do that. And you can just grab a piece of fruit, wherever you want. There's some sandwich, and there are also some cake and also some drinks. So just grab wherever you want, and there's a bath provided for you. So you can have the lunch either upstairs or here, wherever you see fit. And then we'll have an earlier start in the afternoon for the next keynote. Okay, so I think it's ready.
Hi, good morning, everybody. My name is Nils Murugarra, and today I'm going to present my work, Image Retrieval with Mixed Initiative and Multimodal Feedback. This is a joint work with Professor Adriana Kowalska. We are from the Department of Computer Science from University of Pittsburgh. First, let's imagine that we really like to find a shoe, okay? And the first question that we can ask is, how can we find a shoe? Or how we can find this shoe? For example, a friend can tell you, oh, draw a sketch and show to another friend. Other can say, oh, describe it to the salesman and compare with another shoe. Even the salesman can come to you and ask you some questions. Is the shoe that you're looking more formal than this other one? These natural interactions have been developed previously in a computer way, and also existing methods use these approaches in an isolation. So if we look in a closer look for the first two, we can say that both are user-initiated methods because the user starts the interaction in the form of a sketch or in a description. Also, we can say that they are exploration-like methods because it helps to reduce the search space and concentrate in certain parts. And the last one is a little different. We can say that we can consider like an external source that could be like the salesman or a computer, that it will exploit some data, some information about a problem, and then it will guide the user to interact. In this case, the guidance is doing by some questions. So in this work, we investigate is there an intelligent way to combine user and system interactions with multimodal feedback. So we want basically to change that or interaction with an interaction. In particular, we can have an agent that adaptively chooses an interaction, and for each interaction, it will assign a score. In this case, the higher score is the first interaction, that is the red arrow. So our key idea is that we like to learn to adaptively combine different forms of user feedback that can be textual or visual for interactive image retrieval. And to select the best feedback, we train a reinforcement learning agent, which finds the target image as fast as possible. So we have our image search here. Then we have one action that could be the free-form attribute feedback. It's like the description that we talked before. Then we have another action that is the suggested question. These suggested questions could be the interaction with the salesman. And then we have the action with the sketch drawing. So let's say that our agent already decides iteration 1 and iteration 2. But at iteration 3, it should to decide which action is the most meaningful at this time. The idea is that the agent should do the less number of iterations as possible, so the target image is found as quickly as possible. So let's compare our work with another work in the literature. First, we are not focused on improving sketch-based retrieval methods. We focus on when to request a sketch. Also, rather than retrieving a single result, our users will perform iterative image retrieval. We have like 10 iterations of updates. The most similar work to us is Chen et al., which also uses reinforcement learning. They have like an instead representation, a reward that is represented with retrieval precision, and then they have some actions. These actions are based on relevance feedback methods, and they are these 3. However, this work only is interested in identifying if image property is defined as desirable or not. However, it does not allow the users to describe comparatively how the results should change. When I mention comparatively, I mean like a comparison between some target image and some reference image that could be done like using attributes. Also, unlike Chen et al., we consider both textual and visual feedback. Let's describe our approach. First, we have our interactions. In this case, we have 2 kinds of interactions, the attribute feedback interactions and the sketch feedback. For the attribute feedback, we are going to have 3 components. We have like the attributes that are in the red box, then we have the reference image that is in the green box, and then we have to provide an answer that is the comparison response in the blue box. So for the freeform attribute feedback, the user needs to provide or choose an attribute and reference image, and after that provide a response. Once we have this knowledge, we can re-rank all the database, all the image database using this knowledge. Then the second action is the suggested question. In this case, the computer provides us some attribute and reference image, and the user only needs to provide a response. Similar, using this knowledge, we are going to update the ranking of the images in the database. The third action is the sketch feedback. For this sketch feedback, we have two options to do this. First, we are going to use a generative adversarial network that in this case we receive a sketch drawing and we are going to color this picture. And the second option is do image retrieval. In this case, we want to learn an embedding that it will makes closer sketch and its corresponding colored picture. Using this information, we can retrieve some colored pictures, receiving an input and a sketch. Using the output of the colored picture from the first branch or the output of the retrieved images, we can learn one class SVM. And then using this class SVM, we can rank all the images in our database. Once we have defined the interactions, now we formulate the problem like a reinforcement learning. And we are going to model using like a Markov decision process. First, let's define the state. The state is represented with the action history. That is like the last 3 actions taken. Also, we have some information about the 20 top images. And we represent some proxy information for the target image in the form of positive proxies and negative proxies. Positive proxies are the 5 nearest neighbors, and negative proxies are the 5 farthest neighbors. Proxies resembles the images provided by users to initiate a search. Then the output of our network will be the actions, the 3 actions that we talked before, and basically it will generate a score for each of the actions. So we are going to pick the action with the highest score. Now that we have the network architecture, we want to guide this network to learn. So to guide the network, we're going to define some rewards. First, the blue box corresponds to a representation of the top images. Then the green boxes are positive proxies, and the red boxes are negative proxies. So in each iteration, first, we want to ensure that the distance to positive proxies should decrease. The distance from the target image to the negative proxies should be increased. And also that in each iteration, we are going to assign a negative reward if the sketch action is queried more than once, because with one time is enough for us. If we have a closer look, we will see that the proxies branches and also the top image branches, first we do like a feature extraction part, and then we do some average on the quantity of the data. And also in this case, we also have like a history information that it has size of 3. And then we apply a convolution on the history data with the features. We believe these convolutions help us to capture knowledge about image features and ordering. Also, we apply some tricks of reinforcement learning like replay memory that help us to collect many instances as the agent is running. And it's also useful to remove short-term correlation. Also, we ensure random actions with probability decreasing from 1 to 0.1 as the agent is learning. We believe that at the beginning, we don't have too much information about the problem, so it's good to do a lot of exploration, so a lot of random actions. But as the agent is learning, it's better to trust much more in the knowledge of our agent because it has already exploited some knowledge. So in the last part, there are less actions only with 10% of probability. Then we want to do some evaluation. First, we have some simulated users, and we are going to evaluate with Whittle search. Whittle search is the free-form attribute feedback that we talked before. Pivot round robin is the suggested question. And then we have another that it's a sketch retrieval. In the first iteration, you draw a sketch, and then we complement with pivot round robin in later iterations. In this case, we have experiment with PubFig dataset. In the x-axis, you can see the iterations, that it goes at maximum on 10. It's the amount of feedback. And then in the y-axis, we consider the accuracy, that is the percentile rank, that higher is the better. So these are the 3 baselines. And then our approach with reinforcement learning outperforms all the other methods by a great margin. Then we have a similar performance for scenes and also for shoes. Now we want to do a more challenge experiment, and in this case we do with live users. So we recruit university and Amazon Mechanical participants to conduct 100 searches. In this case, users provide a sketch and attribute feedback, and it's also worth to know that the sketch provide high quality data. For example, there are some drawings of the flat shoe that they have some big details like the flower ornaments, or some details on the boots like the shoelaces in the top and in the middle. Then to incorporate our reinforcement learning agent, we develop a web interface, and it queries the next action using a REST API. We verify the benefit of our adaptive feedback strategy in this realistic scenario. First, we update the x-axis with the time taken per iteration. So for now, we can observe that the best method is vital search, but it requires much more time than the other methods. Now, our proposed work achieves similar performance to vital search, but it requires less amount of time. And also, if we observe some iteration, for example, the person interacts 75, we achieve in 50 seconds faster than the vital search method. Then we want also to analyze some of the actions of how the agent is learning. So we observe first that the sketch and vital search actions are mainly performing iterations 1 and 2, which are highlighted with the sky blue and blue colors. These are kind of exploration-like actions. And then after iteration 3, we observe that the pivot round robin is the most common one, that is with the white bar. So we can infer that our reinforcement learning agent learned to prioritize human-initiated feedback early on and complement with matching-initiated feedback in later iterations. Also from our sketch-to-photo-generated images, we can observe that the most realistic corresponds to Pufik, then shoes, and finally scenes. Even if scenes didn't do a very good job, it captures some information about the color of the sun, the color of the highway, the color of the forest. Also, this order corresponds to the relative performance of our method, which was best in Pufik and shoes. So to conclude, we explored choosing interactions in a mixed initiative image retrieval system. Our approach selects the most appropriate interaction per iteration using reinforcement learning. And our model combines human-initiated feedback with matching-based feedback for faster retrieval. And we'll perform standard image retrieval methods with real and simulated users. Thank you very much for your attention, and I am happy to answer any of your questions.
Thank you, Niels. We have time for one question. Making my life very hard. So, actually, I have two. Can you combine them? Your features, your attributes?
Sorry?
Can you combine them?
The sketch and the attribute feedback? Yes, basically I generate like a probability for the, I think I have in this slide. I have like a probability for the, when I use like the sketch feedback, and I have also probability for the attribute. So basically it's like a multiplication of probabilities. Okay. And to avoid like the floating error, we can transform with a log function.
Okay. I noticed in your experiments that you said that you're using edges, like synthetic edges.
Yeah, for the simulated.
But actually, that's not what the users do.
Yeah,
is it somehow a way you can introduce some noise in the learning process to try to come closer to what the users might do? Will it be working?
Sometimes when there's, I think we use like the HAD for the feature for the edge detection. There's some way that you can get like some more finer detail or grosser detail. I think that would be a way to introduce some kind of noise.
Okay, right. Thanks. If anybody else, going once, going twice. Orals are over. Thank you very much for staying with us. Enjoy the lunch.